Well, it is Tuesday morning. You guys had a nice 4-day weekend. I hope you enjoyed the weather, got outside, had some fun with friends, family, and maintained social distancing and all those rules that we're following to keep everybody safe, but still having a good time. So we are nearing the end of the journey here. We've got I think about 10 days left of content and then we're done. Holy smokes. So if you read my weekly summary, you'll see I put a timeline in there of approximately when we're going to be finished. So that's kind of exciting for you guys and nice to be done. Chem 30. It's been a long, challenging journey, especially the switch to online hasn't been easy for anybody, including myself, but we're getting close. So good job, hang in there and keep pushing to the finish and we'll be done before you know it. So today's lesson is actually a nice, easy one. I like it. It's kind of simple, but it's also interesting. So in Chem 20, you guys learned about acids and bases and you use the Arrhenius definition or the modified Arrhenius definition. And in Chemistry 30, we use a different model to describe them that is a little better in that it covers more acids and bases, and it's actually a little simpler, which is kind of strange when you think about it, that in Chem 30 it gets easier instead of harder than Chem 20. So this theory is called the Bronsted-Lowry theory, named after Johannes Bronsted and Thomas Lowry. And it allows us to describe more acids and bases than you could using your Chem 20 knowledge. So the theory is simple. Acids are proton donors and bases are proton acceptors. And I forgot to give you pages in your notes. And those pages are, oh my gosh, if I could find them. It's unfortunate that I am not organized and don't have those for you. Okay, there we go. So we're working on page 322. Page 300 and, no, I lied. Page 317. Page 317, Bronsted-Lowry theory. Okay. So acids are proton donors, bases are proton acceptors, and amphoteric, or you'll see the term amphiprotic, are chemicals that can act as both an acid and a base. They can donate or accept a proton. So that's kind of like in redox chemistry when we had multivalent metals, and those metals could gain or lose an electron, so they could be an oxidizing or reducing agent. For example, Fe2 plus could gain 2 electrons and become Fe solid, or Fe2 plus could lose 1 electron and become Fe3 plus. So now we have acids that are in that similar position and bases. They can both gain and lose. All right, so let's dig into this. Using their theory, classify the following reactants as acid, base, or amphoteric. So H3O plus is donating a proton. So you'll see this kind of looks a little bit like redox, but instead of an electron, we're keeping track of a proton. So H3O plus is donating a proton, which would make it an acid. And NH3 is accepting the proton, which makes it a Bronsted-Lowry base. Okay, looking at this one, NH3 again is accepting the proton, so it's a Bronsted-Lowry base. And water is donating, so water in this example is a Bronsted-Lowry acid. That's interesting that acid, or that water can be an acid. And here we have water accepting a proton. So in this example, water is a base. Wow, interesting. And HCl is donating, so it's an acid. So water can be both an acid and a base. In other words, water is amphoteric. And if you remember from redox, water was also an oxidizing agent and a reducing agent. It was very weak. And for acid-base chemistry, it's also a very weak acid and a very weak base. But it can do both, donate and accept, so amphoteric. Okay, here we have HCl as an acid donating and NH3 as the base accepting. Okay, now in these examples, there's no arrows drawn in. So if you want to pause the video and draw the arrows in, figure it out yourself, you can do that. The trick is to find a reactant and find its partner on the product side and then see what happened to it. So HCl3 minus became CO3 minus. So how did it do that? It lost or donated a proton. And water accepted the proton. So if water gains an H plus, it becomes H3O plus. Okay, so that makes HCl3 minus our acid donor, and water is the base, the acceptor. Okay, here's another example. HCl3 minus, what does it do? It turns into H2CO3 minus. So how do you get from HCl3 minus to H2CO3? You would have to accept a proton, which means in this example, water is donating it. So water is the acid, HCl3 minus is the base. Okay, so if you look at HCl3 minus, it is also an acid and a base. It is also amphoteric, capable of both accepting and donating a proton. What happens to water when it loses an H plus? Turns into hydroxide. Okay, so far so good. All right, reverse reactions and conjugate pairs. So as you learned in chapter 15, not all reactions are quantitative. Some of them can be stuck in equilibrium, they can move in reverse, they can be going back and forth. So because they can move in reverse or be moving in either direction to reach equilibrium, we can classify the products as well. So let's take a look at this example. Water is donating, it is an acid. Ammonia is accepting, it is a base. If we look at the reaction in reverse, we can classify these as well. So what's happening here? NH4 plus turned into NH3. So how did it do that? It donated a proton. Now, instead of calling it just an acid, we have to recognize that it's on the product side. So we call it a conjugate acid. And in this example, hydroxide is acting as the base accepting, so it is the conjugate base. Now, conjugate means partner. So this conjugate base has a partner right here, which is an acid. So every acid has a conjugate base, and every base has a conjugate acid. So they're partners. And if you look at the pair, NH3, NH4 plus, a conjugate pair always differs by a proton. That's it. Differs by one H plus. So here is our base and conjugate acid, and our other conjugate pair is H2O and OH minus. So this is the acid and this is the conjugate base. Okay, so you can always recognize conjugate pairs because the only thing different about them is a single proton. So it's actually pretty easy. Okay, what have we got going on here? An acid in the forward reaction always produces a base as its product, and the pair is called a conjugate pair. So acid and conjugate base, which we just did. And same thing, a base in the forward reaction produces a conjugate acid as its partner. And we've already talked about all of that too. So we are good to go. Everybody happy? Bronsted Lowry theory, pretty easy. All right, for the following reactions, I want you to label the acid and its conjugate base and the base and its conjugate acid and show the proton transfer. So again, compare the two entities on opposite sides that are linked. So this is going to be a pair. So HCl3 minus and CO3 minus, this has the extra proton, so that makes this the acid, which means this is its conjugate base. And if this is an acid, this must be a base. And since this is the acid, it's donating its proton to the base. And if this is a base, here's its partner, which must be a conjugate acid. And again, in reverse, this conjugate acid donates its proton to the conjugate base. Okay, so try the second one on your own. And water turns into hydronium. So this is the base and this is the conjugate acid. If I put some arrows in, acid donates the proton to the base. Conjugate acid donates the proton to the conjugate base. So easy. Love Bronsted Lowry theory. Okay, like halfway done here. Okay, using the general formula for acids, show how an acid can be amphoteric. Remember H2TB from the Le Chatelier lab. Okay, so how can an acid be amphoteric? So in order for an acid to be amphoteric, it has to be able to donate a proton. So it has to have an H. And it has to have a minus charge in order to accept. So this is kind of the generic pattern for an amphoteric compound. So in water or any other substance, it can donate a proton. X2 minus and hydronium. That's what makes it an acid. It forms hydronium. In water or any other compound, it can also accept because it's got a minus. It will attract a proton. So it becomes H2X and hydroxide, which is why it's acting as a base. It's creating a basic solution. So H2X can go to HX minus, which can go to X2 minus, and this is the amphoteric one. And here we have strictly an acid, and here we have strictly a base, and in the middle we have an acid-base combo. It can do both. So what's the generalization you can make about HX minus ions? Both acid and base. Okay, X minus or X2 minus. What generalization could you make about those? Are they acids or bases or amphoteric? They have no protons to donate, so they can only be bases. Except H plus. So as a rule, anything that has a minus or any anion can act as a base, and 2 minus or 3 minus tend to make good bases because they have strong pull for protons, positive protons. It's all about attraction, repulsion. Okay, moving along. Ho, this can be a short lesson today. Some key ideas. A strong acid has a very weak attraction for protons. A strong acid. So hydrochloric acid is a strong acid. Okay. It is not interested in attracting protons. What does it do instead? Gives them up. What percentage of its protons does it give up if it's a strong acid? 100%. 100% of them. Okay. A strong base has a very strong attraction for protons. The strongest bases are OH minus. And they will rip a proton from anything to make water. The stronger the acid, the more weakly it holds its proton. Okay, so if I draw HCl with that molecular bond or that covalent bond, the Cl has a very high electronegativity. which means it pulls hard on this electron pair and forms a Cl minus, leaving H plus by itself. How often does it do that? 100% of the time. So anything that has a really strong pull for the electron pair makes a great acid because it pulls the electrons away and leaves the H plus as the acidic ion. And the last one, the stronger the acid, the weaker its conjugate base. Interesting. So the stronger the acid, so HCl as a strong acid makes Cl minus and H3O plus. So it's a strong acid, and here's its conjugate base. This reaction goes 100%. In other words, there is no reverse reaction. Cl minus will not accept protons. Okay, HCl gives them up, Cl minus does not accept them. This reaction does not go in reverse. So strong acids have really, really weak conjugate bases. So those are 3 key ideas for you to think about. Bright idea. Or somebody pulling up their pants. Terrible joke. I know. Okay. Using Bronsted Lowry theory, how would you classify water in the following reaction? So take a look at the reaction. What would you call water here, and what would you call water here? So what's going on? Water is becoming H3O plus. How does it do that? It has to accept an H plus. So it's acting as a base. And here water is turning into OH minus. How does it get to OH minus? It must donate an H plus. So here it's acting as an acid. And here it's acting as a base. Who is a stronger acid, HNO3 or H3O plus? So that's a good question. HNO3 or H3O plus? So in this reaction, they've given us arrows that show us that the forward reaction is happening at a greater rate than reverse. In other words, this reaction favors forward. So if it favors forward, which of these 2 acids is stronger? HNO3 wins the battle and moves forward. Very few of the hydronium move in reverse. Okay, does HNO3 have a strong or weak attraction for its proton? Well, if it's a strong acid, it will have a weak attraction for its proton. Does NO3 minus have a strong or weak attraction for a proton? Okay, well, if the reaction doesn't move in reverse very much, what does that tell us about the strength of this to accept a proton from hydronium if it doesn't really move in reverse? That means NO3 minus has a weak attraction for a proton. So HNO3 minus is a strong acid, NO3 minus is a weak conjugate base. And ladies and gentlemen, that is it. Textbook questions for you to practice this concept. And there's 1 page in your study guide. And I did have this organized. I think it was 364. And I will put the answer key to that one online for you so that you can check it. Yep, page 364. And these textbook questions, the answers are on these next 2 slides. So if you want to try the questions and then you can go back to this and take a look, you can see the answers right there, numbers 2, 3, and 4. And page 726. So you could do either one of those assignments would be enough practice, either the textbook questions or the study guide page. I don't think you need to do both. It's up to you. The more practice, the better. Your call. It's beautiful weather outside and you got a lot on the go. Just do one of them. And if you feel like you got it dialed in, you're good to go. Okay, I'm going to stop there. tomorrow we will finish off Bronsted Lowry theory. And what's the second thing we're going to look at? We're going to start calculating pH, POH for these reactions. And then Thursday, we're wrapping up the week. Short but sweet.